So what I have over here is a bowling ball, and let's say that I throw the bowling ball onto the floor, and let's say that in it initially has a velocity of v naught, which is v subscript 0, or just v0, and that's the initial velocity. And let's say that when I throw down the bowling ball, it's going to have an initial velocity, and it's also going to have no rotation. So it's just initially going to translate only with an initial translational velocity, and it's not rotating. And let's say that the coefficient of kinetic friction, or the force of kinetic friction, is denoted with F subscript K for force of kinetic friction. And some things I want to analyze in this video is the motion of the bowling ball initially and later on. So initially, when I throw down the bowling ball and it translates only, is the ball slipping, or is the ball rolling without slipping? Or in other words, is the non-slip condition satisfied? And I went over this condition in an earlier video, so make sure you watch that before you watch this, where I talk about the non-slip condition in there. And what is the non-slip condition? So the non-slip condition is just a condition that has to be met in order for an object to not slip. Or in other words, the non-slip condition is just a condition that has to be met in order for an object to roll without slipping. So the actual non-slip condition is this: that the velocity of the center of mass of the object is equal to the radius of the object times its angular speed. And this condition has to be met in order for the object to not slip. Meaning, if we want an object to not slip, this condition has to be satisfied, meaning the velocity of the center of mass has to equal r times the angular speed, or the radius times the angular speed. And if this condition is satisfied, then we know that the object will not slip. Now, what about if the condition was not satisfied? Meaning if the velocity of the center of mass did not equal the radius of the ball times its angular speed. So if this condition is not satisfied, then that means that the ball will slip. And so in this case of the bowling ball that has an initial velocity but no rotation, is the non-slip condition satisfied, or is it not satisfied? Or in other words, is the non-slip condition, does it hold or does it not hold? And so let's look at this. So we're analyzing the bowling ball initially, meaning as soon as it touches the floor, we want to analyze that initially, or the initial state of the bowling ball. So the question we're asking is, does the velocity of the center of mass of the bowling ball equal the radius of the bowling ball times its initial angular speed? And so what's the initial velocity of the center of mass? That was already given to us, and the initial velocity of the center of mass is just v naught, or v0. And that's because the center of mass is initially traveling at a speed of v naught. as soon as it touches the floor, that is. And what about the angular speed? And the angular speed initially is 0. And that's because in the problem it already said that the ball had no initial rotation. It said that initially there is a v naught, but there is no rotation. So if there is no rotation, that means that the angular speed is equal to 0. So if we multiply this radius r times 0, then we just get 0. So does the left-hand side of the equation equal the right-hand side? Or in other words, does this condition hold? So does v naught equal the right-hand side of the equation? And the answer is no, because v naught is given to us in the problem, and the right-hand side of the equation is 0, because the angular speed is 0. So if we multiply the radius r by 0, we just get 0. So this condition is not satisfied. So in other words, the non-slip condition is not satisfied. So since the non-slip condition is not satisfied, what we can write is that the velocity of the center mass, we already know that the velocity of the center mass does not equal the radius times the angular speed. And what we can write is that the velocity of the center mass is greater than the radius times the angular speed, because we know that the velocity of the center mass is just equal to the initial velocity, and the initial angular speed is 0. So because r times the angular speed is 0, and because the initial angular speed is 0, and so the velocity of center mass is greater than 0, which is a true statement. And so since the velocity of the center of mass initially is greater than the radius times the angular speed, then what will happen is that, notice in my diagram that there's a force of kinetic friction, which is F subscript K for force of kinetic friction. Then what will happen is that the force of kinetic friction will actually decrease the velocity of the center of mass, and it will try to increase the angular speed until this condition right here is satisfied, or until the non-slip condition is satisfied. Now, why is this? So initially we know that the velocity of the center of mass is greater than r times the angular speed. So the force of kinetic friction will try to decrease the velocity, the high velocity of the center of mass, and it will try to increase the small angular speed of the object until the non-slip condition is satisfied, or until the velocity of the center of mass equals r times the angular speed. So, or in other words, the force of kinetic friction just wants this condition, the non-slip condition, to be satisfied. That's all the force of kinetic friction is trying to do. It just wants the non-slip condition to be satisfied so that the object can not slip. And so the force of kinetic friction will continue to decrease the velocity of the center of mass and it will increase the angular speed until the non-slip condition is satisfied. And notice that the force of kinetic friction is pointing opposite to the velocity. And since the force of kinetic friction points opposite to the velocity, it's going to decrease the velocity of the center of mass because the friction is pointing opposite to the velocity. And that'll decrease the velocity of the center of mass, and in return, it's going to increase the angular speed. So, because of friction, the velocity of the center of mass will decrease, and in return, it's going to increase the angular speed by creating a torque. So, using all of this information about the non-slip condition, let's now try to find the amount of time that it takes for the ball to go from its initial state of rolling with slipping until its final state in which the ball rolls without slipping. Or in other words, let's find the amount of time that the force of kinetic friction will take in order to cause the velocity to decrease and increase the angular velocity. Because as I wrote over here, the force of kinetic friction will decrease the velocity and it will try to increase the angular velocity until the non-slip condition is satisfied. And so that's what I want to find. I want to find out how much time does that take? Or in other words, I want to find out how long does it take for the force of kinetic friction to decrease the velocity enough so that it's equal to the radius times the angular speed. So I want to find the amount of time it takes for the object to go from its non-slipping, or it goes from its slipping state to its non-slipping state. So as I wrote over here, I want to find the amount of time that the ball rolls with slipping. Or in other words, I just want to find the amount of time that the ball slips from its initial point of when I throw the ball down to its final point of rolling without slipping. And so let's look at the ball initially. Initially, when I throw down the ball, it's going to, and let's look at the final position as well. And the final position is the point at which the ball rolls without slipping. And the initial position is when the ball is rolling with slipping. And so as we found out in the few moments of previously, we knew that the velocity of the center mass is actually greater than the radius times the angular speed. And we just found out that a few moments ago where we analyzed the non-slip condition. And so over here the object is rolling with slipping. But over here the object is rolling without slipping. And we're given that the object travels at an initial velocity of v naught or v0. And after some time, it's going to reach a final velocity. Let's denote that with the v subscript f for Vf. And so since the object is rolling without slipping, what we know is that the velocity of the center mass is equal to the radius times the angular speed. And this is the non-slip condition. And so this condition has to be satisfied in order for the object to roll without slipping. And so the final velocity is just denoted with Vf. And what I want to find right here is how long does it take for the object to go from its initial state of rolling with slipping to its final state of rolling without slipping. Or in other words, how long does it take for the object to go from the initial to the final state? Or how long does it take to go from rolling with slipping to rolling without slipping? That's what I want to find. I want to find that amount of time, t. And so we can use kinematic equations to find the time that the ball rolls, but there is something else that we need to find first. We need to find the acceleration of the ball. And we need to find the acceleration because notice that there's a force of kinetic friction acting on the object. And so that force of kinetic friction is going to cause an acceleration. And so we would have to take that into account. So the kinematic equation that we can use is that the final velocity is equal to the initial velocity plus the acceleration times the time. And we're trying to find the time, but the issue is we don't know the acceleration of the object as it goes from its initial state to its final state. And so I need to find this acceleration. And so this acceleration is due to the force of kinetic friction, which I circled on the diagram. And so the force of kinetic friction is the net force, and that's what's creating the acceleration. So since the force of kinetic friction is the net force, we have to use Newton's second law since there's a net force involved and we're trying to find the acceleration. And so what we can write from this is that the sum of the forces acting on the bowling ball is equal to just ma, or the mass of the ball, times the acceleration of the center of mass of the ball, which is just Newton's second law, which is F equals ma, and that's equal to the force, or the net force, that's acting on the object, which is the force of kinetic friction. And since the force of kinetic friction points in the opposite direction to the motion of the bowling ball, we would have to put a negative sign in front of this. Since the force of kinetic friction is slowing down the bowling ball, or it's opposing the velocity of the bowling ball. That's why we put a negative sign, because the frictional force is opposing the motion of the bowling ball. And so if we expand this out, we know that the formula for the frictional force is just equal to the coefficient of friction, which is mu, times the normal force. And the normal force in this case is just the mass of the bowling ball times the acceleration due to gravity. And if we divide both sides by the mass m, we get that the coefficient of kinetic friction times the acceleration due to gravity equals the acceleration of the center of mass. And so once again, the formula for the force of kinetic friction is just the coefficient of friction times the normal force. And so notice that the acceleration here is negative. And so since the acceleration is negative, that means that the object is actually slowing down, which makes sense because initially the ball is traveling at a very high initial velocity, but then the frictional force is going to slow down the ball as it travels farther and farther. That's why the acceleration is negative, because the bowling ball is being slowed down by the frictional force. And so going back to the formula for the force of kinetic friction, Fn is just equal to the normal force, which is mg. So this is the formula for the acceleration of the center of mass. And so now we can just plug in this acceleration for the center of mass into our earlier kinematic equation. And so now, since we have the formula for the acceleration of the center of mass of the bowling ball, let's now look more closely into the final state of the bowling ball when it rolls without slipping. So we said that when an object rolls without slipping, the non-slip condition is satisfied. So that means that the bowling ball will reach a final velocity at that point. So we can just apply this kinematic equation. And now we know the formula for the acceleration, so we can just plug that in. And if we plug in the acceleration, we get this formula right here. And so remember that for an object that rolls without slipping, that this condition right here is going to be satisfied. And this is the non-slip condition. So this means that for an object that rolls without slipping, this condition has to be satisfied. So we have to apply this non-slip condition into our kinematic formulas. We have to somehow combine this formula into our kinematic formulas in order to satisfy the non-slip condition. And so recall back earlier that for the initial state of the object, the non-slip condition was not satisfied because the velocity of the center mass was greater than r times the angular speed. And so notice that in the final state of the object, the velocity of the center of mass is going to reach a final velocity because it's going to become decreased by the force of kinetic friction. So it's going to reach a final velocity. And so I can just say that the final velocity is equal to the velocity of the center of mass, and that's equal to r times the angular speed. And so I'm just rewriting the non-slip condition. And so the velocity of the center of mass is equal to the final velocity. Since the object in the final state is beginning to roll without slipping. And all of this just equals the non-slip condition. And so notice that this velocity of the center of mass, since that equals the final velocity, that has to equal this entire expression right here. So we can just plug in this entire expression into our velocity of the center of mass. And if we do that, we get that the following expression, and that's equal to r times the angular speed. Now, what is this angular speed? How do we find that angular speed? And so the angular speed is just an expression for the angular speed as the ball goes from its initial state to its final state. So we just need to come up with an expression for the angular speed of the ball as it goes from its initial state of rolling with slipping to its final state of rolling without slipping. And so I'll denote that with the angular speed subscript f for final angular speed. So notice that the initial angular speed is 0. The final angular speed is not going to be 0 because the force of kinetic friction is going to create a torque. It's going to generate a torque, and in return, that torque is going to increase the angular speed. So the ball will have a final angular speed, and I'll denote that with a angular speed subscript f for final angular speed. So the initial angular speed is 0, but the final angular speed will have some value. And so note that I can also use angular or rotational kinematics to find an expression for the final angular speed. So I can write just a rotational equivalent of this formula right here. So I can just say that the final angular speed is equal to the initial angular speed plus, and the rotational equivalent of acceleration is just the angular speed times the time. And you can usually find these kinematic equations on any formula sheet for physics. And so I can just plug in that expression into this variable right here. And so note that I'm just finding an alternative expression for the final angular speed of the ball as it goes from its initial state to its final state. So if I just plug in that formula, I get the following. But now we have a new problem. We don't know what the variable angular for the angular acceleration is. So now we have to find an alternative expression for the angular acceleration in terms of our other given variables. So recall that when we used the Newton's second law for acceleration, or to come up with an expression for the acceleration of the center of mass. And so we just applied Newton's second law, and we set that equal to the force of kinetic friction to come up with an expression for the acceleration of the center of mass. Now, how do we come up with an expression for the angular acceleration? So now we have to use Newton's second law, but for rotation. And now this formula is really similar to Newton's normal second law, but it says that the sum of the torques is equal to the moment of inertia of the object about its center of mass times its angular acceleration, and we use this for since we're trying to find the angular acceleration. So earlier we used sum of the forces equals ma for the acceleration of the center of mass, but now we have to use the sum of the torques equals the moment of inertia times the angular speed to find an expression for the angular speed. So let's apply this formula. So the sum of the torques is equal to the moment of inertia of the object times the angular acceleration. And we know that the torque, the formula for the torque is just equal to the force that's creating the torque times the distance that force is from the axis of rotation, which is the variable r. So torque is equal to r times F. And the variable r in this case is just the radius r. And the force F is equal to whatever force that's causing the torque. So we know that the radius is r. Now the force that's causing this torque, or the force that's causing the object to spin, is just the force of kinetic friction, because that's the net force that's acting on the object. And the force of kinetic friction is acting at a distance r from the axis of rotation. That's why we multiplied it by the radius r. Now, if you look on any formula sheet for physics, the moment of inertia of a sphere about its center of mass is just 2/5 times its radius squared times its angular acceleration, and that's equal to r times, and the formula for the force of kinetic friction is just equal to the coefficient of the kinetic friction times the normal force, which is just mg. And remember that we're solving for the angular acceleration, and if we simplify this down a bit further and solve for the angular acceleration, we'll get the following formula. So right now we're just isolating for the angular acceleration, and we have this formula right here. So this is the formula that we can substitute in to our earlier expression, because this is the angular acceleration that the ball undergoes as it goes from its initial state to its final state. So if we plug in that expression for the angular acceleration, we'll get this expression right here. So all I did was just distribute this r into the parentheses, and I plugged in the expression that we derived for the angular acceleration. And now let's simplify this down a bit further. So notice that in the beginning I said that initially the ball has only v naught, so it only has translational velocity and it has no rotation. So it has only v naught and no rotation, meaning that the initial angular speed is 0, meaning this term right here goes to 0, because multiplying an angular speed of 0 times r gives us 0. So that expression, that term right there, all goes to 0. And if we simplify this down a bit further, let's bring this term over to that side. And notice that the numerator has an r and the denominator also has an r, and those two will just cancel out. And now notice that these terms we can actually combine these terms since they both have like terms. And if we get common denominators for the fractions, the common denominator is 2. So if we do that, then it would be 7/2 times the coefficient of kinetic friction times the acceleration due to gravity times t. And remember that we're solving for the variable t. And so let's isolate that by multiplying both sides by the reciprocal of this fraction and dividing both sides by mu k and g. And if we do that, we would just get that the time is equal to 2 over 7 coefficient of kinetic friction times g times the initial velocity. And so this right here is the time that the ball rolls with slipping. So if we were to interpret what this expression for the time represents, so this variable t just represents how long it took for the ball to go from its initial state all the way to its final state. Or in other words, how long did it take for the ball to go from its rolling with slipping state to its rolling without slipping state. And so this distance right here just represents the amount of time it took for the ball or the bowling ball to go from rolling with slipping to rolling without slipping. So I'll write it in words here. So the time t represents the time that the ball slides, or in other words, rolls with slipping. Rolls with slipping and sliding are the same thing. So the time t represents the time to go from rolling with slipping to rolling without slipping. That's what the variable t represents. The amount of time it took to go from its initial state of rolling with slipping to rolling without slipping. Now, how could we use the non-slip condition? Or how could we interpret this using the non-slip condition? So note that initially the velocity of the center of mass was greater than the radius times the angular speed. And that's because the angular speed was 0 and the initial velocity was greater than 0. And so since this was the case, that means that the non-slip condition was not satisfied. So then the force of kinetic friction is going to try to oppose this velocity. It's going to decrease this velocity, or in other words, it's going to slow down the bowling ball, and in turn it's going to increase the angular speed. And it's going to increase the angular speed by creating a torque. And since the frictional force acts at a distance from the axis of rotation, it generates a torque, and that causes the object to rotate. And that's what increases the angular speed. So the force of kinetic friction decreases the velocity of the center of mass, and it increases the angular speed until the non-slip condition is satisfied, or until this condition right here is met, that the velocity of the center of mass has to equal r times the angular speed. Once this condition is met, then the force of kinetic friction will stop acting on it, since the ball is just going to roll without slipping. And so another interpretation is the force of kinetic friction is going to decrease the velocity of the center of mass, and it's going to increase the angular speed until the non-slip condition is satisfied. And all of that is going to take a time of this expression right here, the expression that we solved for. So another interpretation is that the force of kinetic friction is going to take this much amount of time to decrease the velocity and increase the angular velocity until this condition right here is satisfied. So there's many interpretations to this time using different factors like the non-slip condition. And so this can also represent just the amount of time it took for the ball to go from rolling with slipping, and then the force of kinetic friction is going to act on it, and then it eventually reaches a final state of rolling without slipping. So that entire process is just takes this amount of time, and that's the variable that we solved for.